So the last part of this chapter deals with aromatic compounds. And as a reminder, this is one of the functional groups we talked about back in chapter 10. But aromatic compounds are compounds that contain a benzene ring, which is also basically a six-membered ring that has three alternating double bonds to make it so that each of the carbons here is basically a carbon with one hydrogen with a double bond to a carbon and a single bond to another carbon. So it's basically a CH double bonded to a CH and then single bonded to a CH. All right, so that's going to be your benzene ring. So aromatic compounds have some very interesting properties, and they're going to be a very common type of compound whenever you start looking at, pharmaceutical drugs. If you remember back when we looked at the Tylenol and aspirin and ibuprofen structures back in chapter 10, like all of those had aromatic rings in them or benzene rings in them. So these are very commonly found in a lot of, pharmaceutical agents and a lot of everyday drugs. All right, so no matter how you draw it, as long as you draw it with the alternating double bonds, it's the same. So it doesn't really matter exactly how you draw it. Now they're going to have very similar physical properties to other hydrocarbons. That is, they're going to have low melting points and boiling points. And they're going to be water insoluble because, again, they're still hydrocarbons, right? They have these interesting characteristics of double bonds, but it's still just a whole bunch of carbons and hydrogens. So to name these benzene rings and the derivatives of them, we're going to go through some new rules, even though they're not really that new. It's just kind of a twist on the stuff that we've already learned. So first off, the way to think about this is think of your benzene ring, which is this part, as your parent chain, right? So think of that as your parent chain, and then to name a benzene ring with one substituent, you basically say whatever the substituent is. In this case, the substituent would be an ethyl group, then benzene. So benzene would be your parent chain, and then the substituent would be an ethyl group. So then you would say ethylbenzene, or butylbenzene, or chlorobenzene, right? So the idea here is that you don't need a number because there's only one group, just like we didn't need a number when naming cycloalkanes if there was only one substituent. All right? Now, here's where it gets a little bit trickier. If you have one of these three common monosubstituted benzenes, so benzenes with one substituent, you have to learn their common names. So you want to learn toluene, you want to learn phenol, and you want to learn aniline, right? Because we're not going to use methylbenzene, and we're not going to use hydroxybenzene, and we're not going to use this aminobenzene. But these are very common substituents and common groups that you're going to see frequently, so we need to learn these three. So a benzene with a methyl group is going to be toluene, a benzene ring with an OH group is going to be a phenol, and a benzene ring with an NH2 group is going to be an aniline. So make sure you commit those to memory. So this gets a star. You need to memorize those. All right? Okay, so whenever you have a polysubstituted benzene and we're trying to name it, we're going to follow the same rule that we talked about with the cycloalkanes, and that is you're going to give the lowest possible numbers around the ring. We're going to alphabetize the substituents. And then the one new thing here is this number 3, and that is that when the substituents are part of common roots, so in other words, you have a toluene, or you have a phenol, or you have an aniline, you're going to basically name the molecule as the parent chain. So the parent chain would be toluene, or the parent chain would be phenol, or the parent chain would be aniline. And by default, that common root substituent, so like the methyl group on toluene, would automatically go on carbon 1. You don't write the 1 on the name, but it's understood that that's going to be at carbon number 1. So it'll make a little more sense whenever we do some examples of this. But these are the rules that you're going to follow for the polysubstituted benzene. So whenever you have a benzene ring with multiple substituents. All right? So here is an example, right? So it's a benzene ring, right? So that's going to be the parent chain. And then the first thing you do once you find that benzene parent chain is you look to see if it's a toluene with a methyl group. an aniline with an NH2 group, or a phenol with an OH group. And in this case, we don't see any of them, so we just kind of move on. And then we're going to say, okay, the way to get the lowest possible numbers around the ring is to put this group at number 1, this group at number 2, and that would mean that chlorine would be at number 4. And then you're going to alphabetize the names, so 4-chloro, because chloro comes first, 1-ethyl, because C then E, and then 2-propyl benzene. Okay, so what if you have another one like this, but now you have one of those common roots? So basically you see your benzene ring as your parent chain, but you notice, right, that one of the substituents is one of those common 3. In this case, we have aniline. So again, you're going to circle it, and you're going to call that aniline. Right, there's your aniline. And again, once you circle your parent chain, in this case the parent chain is going to be aniline, we don't have to name that anymore. Now, whenever you have one of those common roots, whether it's toluene with the methyl group, whether it's aniline like this one with the NH2 group, or whether it would be a phenol with an OH group, that automatically goes to position 1. Right, so right there, that's automatically going to be position 1 because of that NH2 there. So then you have to go around the ring and still you want to give it the lowest possible number. So in this case, we're going to go counterclockwise to get the numbers 2 and 5. Because if we were to go clockwise, we would end up with 3 and 6. So 2 plus 5 is 7, 3 plus 6 is 9. We want to go the lowest possible number. So in this case, we would have 2,5 dichloroaniline as our final name. All right, so here's a few others to practice naming. So the first one here, you might be like, what in the world is that thing? That's just another way to represent a benzene ring, and I wanted to put that on there just so I could tell you, just in case you ever saw it somewhere, and you're like, what in the world is that? You can always say, oh, Dr. Witherow said that's a benzene ring. So that's a benzene ring. It's the exact same thing as that. It's just a different nomenclature for it. So those are your benzene rings. So for this first one, you have a benzene ring, right? However, it's not just a benzene ring. It's a benzene ring attached to a CH3 group. So that is going to be our parent chain. So a benzene ring attached to a CH3 group, right, attached to a methyl group is going to be toluene. Toluene, okay? So now if that toluene automatically gets to be position 1, right? So that means that this substituent over here is going to go on position 3. And now we just got to figure out what that substituent is. Well, it's a 1 carbon, 2 carbon, 3 carbon long substituent. 3 carbon long is propyl, so we would call this 3-propyl toluene. And again, you don't need the number 1 for the toluene because it's understood that methyl group has to be at carbon number 1. All right, so now let's look at the one on the bottom here. Again, I see the benzene ring, and the first thing I do is I look for one of those common roots, and once again I have it, right? Here's a benzene ring with one of the common roots. This time it's going to be phenol. All right, now I have to figure out how to number them, right? Knowing I have 2 more substituents. Well, if I go counterclockwise, it would be 1, 2, 3, 4, and 5, right? Oh, nope, that's not right at all. Whoops. Wouldn't be 1. 1 automatically goes on your OH. So that's 1, 2, 3, 4, 5, and 6. That's better. So in this case, the substituents would be on groups 4 and 5. However, that's not going to be right, because if we go the other way around, right, 4 and 5 would have added up to 9. So if we go this way, they'd be on 1, 2, chlorine would be 3, bromine would be 4, right? So in this case, they would add up to 7. So it's going to be a chlorine on 3, a bromine on 4. So how do we name that? Well, we're going to go alphabetical order. So it's going to be 4 bromo, 3 chlorophenol, right? And that's going to be your final answer for that one. And now if we look at the ones on the right where we have to draw the structure, 2,3,5-trimethylphenol. So, and let's not even worry about this one because this is different nomenclature than what we're going to use now. 2,3,5-trimethylphenol. So 2,3,5-trimethylphenol. The first thing we have to do is draw a phenol group. So we're going to draw our benzene ring. That's a 6-membered ring like this, right? That has an OH. And it doesn't matter where we put the OH, but wherever it is we put it, it's automatically going to be position 1. So let's go ahead and put it up there, all right? So that's going to be position 1. Now we have 2,3,5-trimethyl. Well, we know the OH is position 1. That's going to be position 2. That's position 3. And that's position 5. And then we can draw methyls on all of those. I also could have left them as skeletal structures with just the line. So either way would have worked correctly for that one. All right, so that's how we're going to name the polysubstituted benzenes. So again, parent chain, look for your benzene ring, but then you're going to look for one of those 3 common ones, the toluene, the phenol, or the aniline. That would be your parent chain. And then it's the same naming rules as whenever we did the cycloalkanes in terms of the lowest possible numbers around the ring, and then you put them in alphabetical order. All right, so just to give you some idea of some other aromatic compounds, so tamoxifen is a common drug that's used for the treatment of breast cancer. So many breast cancers are dependent on estrogen, so tamoxifen kind of interferes with that whole process. And you can see tamoxifen actually has 1, 2, 3 different aromatic groups. So it's again a chemical that's used that is a good example of something that has aromatic groups. And just to give you some idea of how complicated this IUPAC naming can get, right? So if you look at that name at the bottom, Z2412-diphenylbutyl-1-enol phenoxy NN-dimethylethanamine. That's why we just use tamoxifen, right? So sometimes these generic names and trade names are a lot easier for a reason. So tamoxifen. But this just gives you another example of a molecule that has aromatic rings in it. And then one that you're probably more familiar with are sunscreens. Hopefully you're more familiar with sunscreens than you are with tamoxifen. Sunscreens, most sunscreens contain benzene. And if you look at a bottle of sunblock or a spray thing of sunblock, and one of the ingredients in there is often going to be PABA or PABA, which is para-aminobenzoic acid. And that para is kind of a shorthand, and sometimes I teach this in this class, but I've been kind of taking it out now, which is why I scratched off that one problem on the previous slide. But para basically means that if you have your aniline, right, if you have your NH2 here, the other group is right across from it. So in this case, this is actually a benzoic acid, and we'll learn exactly what that is in chapter 13. But para just means that those 2 groups are opposite of each other. But again, it's a compound that has an aromatic ring in it, and a lot of sunblocks will contain this PABA, and even some sunblocks contain derivatives of it that work the same way. And a lot of phenols actually are very common in nature. So again, a phenol is going to be a benzene ring with an OH. So vanillin is something that like a vanilla extract would come from. So again, you can see that that compound is one of these aromatic compounds that we've been talking about, occurring naturally, and again is used in a variety of different things that we can extract it from nature and use it to cook, for instance. All right, so that should be it for chapter 11.